we're going to apply this to a new model system. We're going to talk about a particle on a ring. Getting more and more atom-like. We're going to find something weird here too. We're going to actually find one of the other quantum numbers. We have only discovered one quantum number so far. Which one have we found? There are 4 quantum numbers, right? What are they? N. What else? M sub L. L. M sub S. We're going to find all of those. Which one have we only talked about so far? N. We're going to skip L. We're going to go right to M sub L. Just kind of weird. You'll see why in a minute. So 2D rotations. Let's talk about a particle on a ring. All right, we're going to consider a particle in a ring. Excuse me, a quantum particle in a ring. With a mass m. The particle moves in a circle having a fixed radius of r. The potential energy is fixed. It's just some number, some arbitrary number. And is arbitrary. Okay. If the potential energy is fixed and it's arbitrary, does that number really matter? No. It just means we'd be adding or subtracting some number over and over again. We care about the relative difference between things here, right? So if you had to pick an arbitrary number to set this to, what would you set it to? Yeah. Set the potential to 0. Why would you set it to 0? Yeah, we don't have to worry about it. Life's easy. It still has some value or could have some value, but if we set it to 0, we don't have to worry. Okay, let's try to draw out this system. We really only have to worry about 2 axes that I'm going to draw. Got x and y. We said that the particle is moving around. Here's our particle. It's traveling in some circle. Got some mass m. And if we were to measure, oh God, I did a terrible job. I want that centered around the axis. I'm going to move this. Sorry. Because I want it more in the center. Okay. That distance there in red, what is that distance? Yep, that's our r. And it's just booping around in a circle, right? What other coordinate would we need to know the location of the particle? So if it's traveling in a circle, we could know x and y, right? But I want to do it in spherical coordinates. What other parameter would I need to know where it is in this plane? Got to know that angle, right? And that's what we're going to call, in this case, phi. So which way it's angled in that spot. Okay. Everybody feel like they understand what the system looks like? It's just a particle on a ring. First question we're going to ask is, what do we always ask for these model systems? What does the Schrodinger equation look like? Okay, tell me the generic Schrodinger equation. Yep. Okay, what can we break H down into? Yep, kinetic energy and potential energy. So you got the kinetic energy operator, potential energy operator, that thing. Okay. That wind is intense. It sounds way too creepy for that wind for how nice it looks outside. Anyways, look at a paper bag, a bird. Okay. Based upon our model system, or the system we're trying to model, can we get rid of anything? Yep. Set the potential energy equal to 0. It's an arbitrary number. Don't need to worry about that. We just have to worry about the kinetic energy operator. Okay, what's the kinetic energy operator going to look like for a 2D system? And I would express this in terms of Cartesian coordinates. We get negative h bar squared. What's over? It's over what? 2m. Yep. And then what else do we need? Yep. Okay. So we could try to do this in terms of Cartesian coordinates. We're used to it. It's nice to deal with it that way. However, if you try it, what happens is x and y are not independent of one another. They're dependent on one another. And in order to know r, you'd have to know the position of both of those. So, problem here, however, cannot separate x and y variables. As if you try to calculate the value of r, you would need to utilize this equation. So we can't do it in this coordinate system. But we just talked about another one. What do you think we're going to do? Yeah. We need spherical polar coordinates. And which ones are we going to need? Yep, r and phi. Okay, to get through this part, what we'll have to do is we'll have to consider angular momentum. Personally, I never paid any attention to angular momentum in my physics classes. You guys might have, or they might have made you do it a lot. I never really got the point of it until I got to quantum, and then I went, ah, crap, that's why I needed all this. I had to learn it all back. Like everybody on my physics classes were mechanical engineers and people obsessed with space. And then there's one really weird kid obsessed with making rides at Disney, where I hope he never got to that point, because he was just constantly failing and asking. So you know how I say I don't remember in my freshman class, I don't remember any dumb questions. I remember his questions, and they were really dumb. Don't tell them I said that, though. All right. I've never had a student ask as bad as questions as him. Let's rephrase it that way. Also, our professor looked like the old guy from Jurassic Park. And yeah. Okay, the oldest looking guy, the one who like opened Jurassic Park, not the new ones, the really old ones from the 90s. It looked exactly like the guy. It's funny. Okay, so we need angular momentum. Do you remember how angular momentum was defined? I think you almost had it, Lily. Yes, it has very different equations for different shapes. The generic equation, though, has a cross product in it. Oh, my ruin. MV cross R. So that's not an X, that's a cross product. Or momentum cross R. So I'm going to highlight that this is not an X. These are cross products. Okay. What do you remember about cross products?
I feel like each thing would.
Yeah, and what are you going to, if you have a scalar or a vector quantity going in, what do you get out? A scalar or a vector? That might be too. Did the mathematicians talk to you guys in those types of terms or not really? Yeah, it's what, 4 years for. Okay, so you're going to get a vector out in the end here. Vectors are valuable because you can break them into individual components. So you can break your momentum in terms of x, y, and z. Break it down that way. That's what we're going to do, and you'll see why we're going to do it that way in a minute. Splitting L into its components. I'm going to do L sub z, or L sub x, L sub y, L sub z. And technically, since these are vectors, I should have vector hats. I'm just being lazy. You'd have y, pz, minus z, py. Ly gets you z, px, minus x, pz. Lz gets you x, py, minus y, px. The clock is 2 minutes behind. Huh. Okay. We're going to use one of these, and we're going to plug it into here and make our lives easier. I promise you it will be easier. Of those three, which one would you select? So I'm going to erase this part. So this is our current Schrodinger equation. We somehow want to get angular momentum in there. So question, which do we want to use? Okay. What would we need to know about y, or I'm sorry, about psi to be able to calculate this? We've got to be able to do derivative with respect to x and derivative with respect to y. That was a terrible 2. So which of the angular momentum components would you pick? Exactly. This last one, because it only depends on x and y or properties associated with x and y. L sub z, as it only has x and y in it. So next question, what would L sub z hat be? So since we're in quantum mechanics, we got to turn everything into an operator. What would LZ hat be as an operator? X is going to become what? X hat, yep, which is still just X at the end. PY, what happens there? Yep, PY hat minus Y hat PX hat. We just put little hats on everything. It's a hat party. Okay, we've seen those before. The position operator in terms of X, what's that one? Just X, yep. Times momentum operator. This one might take a little bit of remembering. It's negative I H bar. What other part do we have in there? Yep. With respect to what? Yep. Minus, we get y times negative I H bar squared. Derivative with respect to what? Yep. Okay, what could we pull out of this thing to make it work a little bit better? Yep. Actually, we're going to leave these as hats. With respect to y minus y hat with respect to x. Okay. We'll figure out why we wanted to do that in a little bit. Let's go back to our Hamiltonian operator. turning Hamiltonian. Oops. We came to a point where we said that's what our Hamiltonian looks like. But what do we want this in terms of? We don't want x and y, but what do we want? Yeah, r and b. So we got to get a little bit closer to that. Okay, I told you this a little bit ago, but recall that we could express, oops, yeah, just make that an x. We could have this in terms of spherical polar coordinates. One over r derivative with respect to r. Right? What things are changing here? Or what things could we change in this expression? What? In this case, we can change the radius, or we're factoring in the radius changing. In our system, is the radius changing? Yep, r is fixed. Therefore, our expression changes a bit. Oops. How would this stuff change if r was fixed? Second derivative with respect to r, if r is a constant. Zero. Is it 0 or is it 1? 0 because it's a constant, right? What happens to this term? All just constants? 0. That's just a constant times this thing. So what we end up with, 1 over r squared, second derivative with respect to phi. Let's take that and plug that into our Hamiltonian. So h hat, we still have that negative h bar squared over 2m. What happens to that derivative? It becomes what? Yeah, a phi. Does that look as bad? Now, instead of differentiating over two things, how many things do we have to differentiate over? Just one. Awesome. So we took something more complicated, and now we only have one variable. One variable is always way easier to deal with than two, right? So this is awesome. Okay. You might be asking, why the hell did we deal with this thing then? We're going to jump back to that in a second. Because what we're going to find is angular momentum is important. It's also quantized for this system. Seems really weird because we've never really experienced quantized momentum or angular momentum before. Okay, so back to this thing. What about LZ? So we came up with an expression that I just erased. Oops, yeah. If you look at this in spherical polar coordinates, what ends up happening is you get that. So it easily transforms over to this guy. And again, we went from 2 variables to 1 variable. And what we're going to find is we can connect these 2 things to each other. Okay, so let's return to the Schrodinger equation. For the system, h psi is equal to e psi. And we got to a point where 2m, I keep making my 2's bad. E squared, put psi up there, is equal to e psi. I'm missing something. What am I missing? Yeah. R squared. Chuck that in there. Okay. From physics, you have the mass times the radius squared. That gets you I. You remember what I was? Moment. Yep. So you could simplify this a bit further. Squared over I. Psi is equal to E psi. Okay, I'm going to ask a series of questions right now that seems like it's not connected, but it will be connected. Oh, should be a 2 there. There we go. What is LZ hat squared? Okay, so remember we said that LZ hat was this. Now I'm asking for that. So all we're going to do in that case, just multiply this together twice. Okay. -1 times -1. 1. I times I. -1. H times H, or H bar times H bar. Yep. Derivative with respect to phi squared. Yep. Okay. We've seen that somewhere before in this expression. Where have we seen this before? It's right here. So therefore, we could express our Schrodinger equation in terms of this momentum, or excuse me, angular momentum. Z hat squared over 2I psi gets us E psi. Or we could leave it just like this. The important point to this is there is angular momentum hidden in here. In quantum systems, we know that they're quantized. So that means there is some form of angular momentum that's quantized in here, which is really weird, meaning there's only specific values that this thing could have to make sure this condition is met. This is how a bunch of forms of different spectroscopy work, which we'll talk about next time. But we now have a valid Schrodinger equation. What's our next step going to be? Yeah, got to get some wave functions. So that's what we're going to focus on next time. Okay. Are there any